It's great to have today's session starting with Ramadas, who probably needs no introduction. He's from CMI, and I'm not going through go through his accomplishments. Instead, I'll give him full time to speak about symplectic geometry of SU2 character varieties and lattice gauge theory, which I suppose I am supposed to know, but I don't know, so I'm going to learn.
Yeah, so there are two phrases there, half of which would be familiar to physicists, the latter half, and the other half to mathematicians, especially differential geometers and topologists. So I have to, so what I have to say about the first is fairly definitive. It is quite nice. It is not incredibly difficult. And what I have to do with the second is fairly there is a clear point, but I don't know if it will lead to anything. But for whatever it's worth, I want to present it. There is a preprint up on the server. So this is the kind of rough plan of the talk. As we go down the page, it will become more and more physics oriented. So symplectic geometry of the SU2 character variety. So a symplectic manifold is a generalization of what physicists call phase space, the cotangent bundle of configuration space. It's a manifold together with structure so that you can define Poisson brackets of functions. And you can, given a function, you can define the corresponding Hamiltonian flow. So all the formalism of Hamiltonian mechanics holds on such a manifold. There is a symplectic manifold which has become quite central over the past few decades. In its algebraic geometric avatar, it was actually discovered in India by Narasimhan and Seshadri. This is the moduli space of stable bundles on a Riemann surface. But it was sort of later realized that it's a symplectic manifold of interest in its own right. And that is the SU2 character variety that I'm talking about. For any compact Lie group, you can have the corresponding character variety. I'm interested in the case of the Lie group SU2. Yeah, so let sigma be a surface. By a surface, I mean a real surface. You will see pictures soon of genus. Genus is the number of holes in the surface. And I take the flat SU2 gauge fields on sigma. For mathematicians, these are connections on the trivial SU2 principal bundle, which are flat. And G is the space of gauge transformations, which acts on the space of connections. The subscript F means these I consider flat connections, curvature 0. So this, even though the space of connections itself is infinite dimensional, after you take the quotient, this is a symplectic manifold with some mild singularities of dimension that depends on the number of holes. It's 6 times G minus 1. So as a symplectic manifold, there is a corresponding volume element, the symplectic volume element, which is preserved by any Hamiltonian flow. That's Liouville's theorem. And because it's essentially compact, this volume is actually finite. And we will assume that by dividing by a constant, it's actually unit. The total volume is 1. So we are, in some sense, talking about probability measures. So now, supposing I have a loop on the surface, and since we are talking about connections, given any loop, I can parallel transport around the loop, so I get an element of SU2, and I can take the trace of that, and that's a function that depends on, if I fix a loop, it's a function on the space of connections. It's gauge invariant, so it becomes a function on the symplectic manifold, and this is sometimes called the Wilson loop function. And it's a function with values in -1, 1, so I can define a real valued function with values in 0, 1. There is some ambiguity at either ends, but we forget about that. That's like choosing a branch of cos. And so, so what you have to take from this is that given any closed loop on the surface, I get a function on my 6 times g minus 1 dimensional symplectic manifold. And this is called the Wilson loop functional, depending on that loop. Now, supposing I'm given a number of disjoint loops. Now, if one loop can be continuously deformed into the other, the holonomy does not change, so the function does not change. So we have to consider loops which are actually cannot be distorted into another, and we will assume that they are non-intersecting. And then it's an interesting fact that you can't find arbitrarily large numbers of such loops. The maximum number is half the dimension of your symplectic manifold. So if the given G, you can find 3 times G minus 1 such loops. If I start with L loops, I can add more to them until I reach 3G minus 1. So this is not coincidental. My symplectic phase space has dimension 6G minus 1, and I can find in many different ways half the number of loops and therefore half the number of such functions on the symplectic manifold. Those of you who are familiar with integrability would already smell something here, and it's true. This is like an integrable system. The Hamiltonian flows corresponding to these loops divide the symplectic manifold generically into nice tori of dimension 3G minus 1, 3 times G minus 1. So so this is a very, very nice integrable system. Now, there is some, so here is let me give you a picture. I will come back to the previous page. So here's just to give some flesh on this. Here is genus 7 surface. So you see 6 holes, but there's an additional hole, the big one. So the genus of this surface is 7. Here is the maximum number of one maximal set of disjoint loops, which give you 18 loops. And you notice that if I look at the region between 3 of these loops, they form what is called a pair of pans. So one of these loops is a waist, and then the other things are the legs of the pans. And these are given by, so you have a certain number of pans stitched together in a certain way. And this is called a pans decomposition of the surface. And these pans decomposition, can be encoded in a graph with a vertex for each of the pair of pans, and 2 vertices are joined if the corresponding pans share a common boundary. So here is the corresponding what's called the Trinian graph. So what do you have to remember? I have just start with the genus G surface. Associated with that, there is a symplectic manifold, the character variety. If I choose a pans decomposition of the surface, or equivalently a maximal set of non-intersecting loops, that is on the one hand encoded by the corresponding graph, and at the same time that gives you an integrable system on this symplectic manifold, which divides it into beautiful tori. So just keep that picture in mind. Let me go back. Sorry? No, there is an edge for each shared boundary. She connect a shared boundary. Thank you. Very good. Now, here is the picture. And this is largely due to William Goldman and then the pair Jeffrey Weitzman. That there is this famous theorem in symplectic geometry called the Doiström-Heckman theorem, which tells you, okay, this is a theorem that even if you don't understand anything else of this talk or forget everything, this is your take home. If I have a compact symplectic manifold of dimension capital 2n, and you have n commuting vector fields on Hamiltonian vector fields on this symplectic manifold, each of which generates an action of the unit circle. So then if you take the corresponding Hamiltonians, you remember the numerology. Dimension is 2n, and I have two capital N, and I have capital N functions. So that means I have a map function from this 2n dimensional symplectic manifold into capital N copies of the real numbers, the n dimensional real vector space R to the n. On the symplectic manifold, I have the Liouville volume. So I can do what the mathematicians call push forward of this volume measure by this map. That basically means that you assign to every tiny volume set in R to the n, the volume of the inverse image of that with respect to this map. So this is called the push forward map of the volume. And the theorem of Dijkstrom-Heckman, a special case, tells you that the image of this map is actually a polyhedron, and the push forward measure is just the standard measure on R to the capital N restricted to this polyhedron. So the very complicated Liouville measure on this capital 2n dimensional symplectic manifold under this push forward becomes just the standard measure on some polyhedron in R to the n. Now what is the significance of that? If I have any function on the symplectic manifold which only depends on this capital N variables, if I want to evaluate the integral on the symplectic manifold, I can remember this only depends on this capital N variable. So it's actually a function on this R to the n pulled back. So I can just restrict that function to this polyhedron and integrate on that polyhedron with respect to the standard stupid measure. If I can handle the geometry of the polyhedron, I can do the integration on the symplectic manifold. So this is the wonderful theorem of Dijkstrom-Heckman. It has infinitely many applications, and so this actually applies here. So as I said, even if you take this away, you would have, I would have. Okay, so now the point is, where was I? Yeah, so there is this Goldman, Jeffrey Weitzman work that actually talks about this specific situation. Take the character variety, look at these maps. Then the image is a very explicitly described polyhedron that I will, polytope that I will describe in the next this thing. And as I said, the implication is that if I take any function of these 3g minus 1 variables and I want to integrate on the symplectic manifold, on the character variety, I can just integrate it on the polyhedron, on the polytope. Now the description of the polytope, how do I describe the polytope? It is described in terms of the Trinian graph. The variables that I am talking about are attached to each edge of the graph, and they each vary from 0 to 1 with the constraint that whenever 3 edges meet at a point at a vertex of the graph, the corresponding variables t1, t2, t3 are obey that spherical triangle equality there. Okay, and one of the key results of my work, which builds on insights from what's called the Verlinde algebra, is that if you take the characteristic function of this polytope in the three-dimensional cube, it has this triple sign expansion that you see there. Okay, that is a key insight. As far as I know, this is not known before, and it is of tremendous use in computations. How much time do I have? Yeah, I have 14 minutes. So let us now compute. I will not actually compute. We can ask, supposing I take n of these loops and look at the product of the corresponding functions, what is the joint distribution of those with respect to this probability measure? In particular, what is the distribution of one of these loops? And you can, thanks to that identity that I put up before, you can actually compute it as a function of the genus, which for some reason here it's called B and not G. And it is that ratio. And when B tends to infinity, that G should be B or B should be G, it tends to this distribution, forget that F here, that is just a test function, it tends to the distribution 2 sine squared pi t1 as a distribution on the unit interval 0, 1. Those who know the Weil measure on SU2 will recognize this. Okay? So even though for finite G it is a complicated ratio, in the limit of large G, out of nowhere you get the Weil measure on the unit interval. So now I come to the lattice theory on a graph. So let gamma lambda be a finite connected graph, which for later reasons, for physics reasons, we will call a lattice. And supposing I'm given a certain number of closed loops called plaquettes. So I've shown those red loops are the plaquettes. So in lattice gauge theory, one is interested in a measure on the space of lattice gauge fields modulo gauge transformation. What is a lattice gauge field? A lattice gauge field is on a graph, is a function from the edges of the graph to a group, in this case SU2, in such a way that if I reverse the orientation of the vertex, the element of the group becomes its inverse. So on the space of lattice gauge fields, there is obvious measure, the product of Haar measures on each of these copies of the group. And lattice gauge theory integrals are of this kind. You take the Haar measure on the product of groups and you have a weight function that looks like that, which I will not go into, and in lattice gauge theory one is interested in integrals of that kind. So now, what do you connect the world of graphs with the world of surfaces? You can do something fairly canonical. Given a graph, you embed it in some three-dimensional manifold, it doesn't matter, you can embed it in R3, and you can take a small enough cumulant neighborhood and take its boundary, and that is a surface, and that's kind of uniquely determined up to, topologically it's uniquely determined. So, and the graph sits inside as what is called the spine of this manifold with boundary. So first of all, by taking a small neighborhood, you get a manifold with boundary, 3 manifold. The boundary is the surface that you are talking about. So this is the link between a graph and a surface. So the graph is the black thing that's called the spine of this 3 manifold, and the boundary is the corresponding surface. So supposing we can lift your plaquettes to closed loops on the surface so that they are mutually non-intersecting. This is not always possible, but it will be possible in at least one very interesting case, which I will show you. I'm skipping over all this. So now here is the crux of the matter. So we have evidence that in the large lambda limit, when the size of the lattice becomes very large, integration over the characteristic with respect to the Liouville measure approximates lattice gauge theoretic integrals, which physicists would understand if they are familiar with it. Mathematicians, I've given such a rush job that I'm afraid that you probably haven't gotten the gist of it. So there is fairly strong evidence that in the limit of large lambda, you can replicate lattice gauge theory integrals in terms of this model on corresponding integrals on symplectic character varieties. And as I said before, for integrals of these objects on character varieties, there is a very beautiful formalism available called the Doiström-Heckman formalism. Now, to put a little flesh on this, let me consider a case of physics interest, namely the three-dimensional periodic lattice. So, in this case, the graph is this trellis of black lines. You should imagine that it's made periodic in all 3 directions. And I have shown 2 of the closed loops, 2 plaquettes that will figure in the action. There are many of them. There are actually 6 of them corresponding to each cube here. Of course, each each of these things is shared between two cubes. So there are 3 times n plaquettes, where n is the number of vertices here. Now, if you pump up the lattice, the corresponding surface looks like this, the surface of this object. And I've shown you the two. So here, remember, there were these 2 plaquettes. If you lift them to the surface, I hope you can see the 2 red squares, one like this and one like this. Now, we need to, so these give you a certain number of non-intersecting loops on the surface, but we need to add some more to them so that I get the maximum number, which is 3 times g minus 1. I've not told you what the genus is here. And to understand that, you have to kind of look at the dual picture, in which case the plaquettes that are already in place are the ones in red, and then you have to add these plaquettes which are in blue, these blue closed loops also. Once you do that at every vertex of this dual picture, you get a complete set of loops. And here is the corresponding Trinian graph. And if you contract the blue edges, you get this cubic lattice. Okay, so now I'm going to lose everybody here, except hopefully 1 or 2 physicists. So in lattice gauge theory, one of the primary starting objects is what's called the partition function, which is the following. So this is generally the case in quantum field theory. So when you have a discretized version of quantum field theory, you have a naive measure, which is the analog of the Liouville measure. And then you have something called the action, and you exponentiate the action. So now you have the naive measure times the exponential of the action, and the integral of this is called the partition function. And for all theoretical investigations, you need to have control. First of all, in field theory, these are horribly ill-defined. You make this defined by making the number of variables finite by first putting your system in a finite box and then discretizing space-time, which is what lattice gauge theory accomplishes. Once you do that, at least you can define this thing called the partition function. But to get control over all the kind of limits that you want to do, infinite volume, ultraviolet, you need to have good control over this thing called the partition function. And it has been a bane in lattice gauge series that these integrals are defined on a fairly large and ill-defined space with a large group of gauge transformations acting on it, so that the partition functions are very hard to write down, let alone manipulate and analyze as an analyst would do, because you need to have serious analysis on this to control the limits that you want to control. So the advantage of all this is that the symplectic versions of this are, thanks to the Doistermaat-Heckman formalism, give you expressions for the symplectic partition function of this kind, where it's complicated, but among its many virtues is that it's a series with non-negative terms, in fact positive terms. So anyone who does analysis knows that if you are going to estimate, it's better to have things without cancellations, without cancellations between positive and negative terms. And so this has that virtue. Then the other big question in the field is the behavior of Wilson loops as the radius of the loops becomes very large. There are similar expressions using the symplectic formalism for those. And there is an analog, you can, those expressions also have this virtue that these involve series with positive terms, okay? So there is there is a significant hope that these are more amenable to analytic explorations of the theory. I think I have, I have come in under the time, so I have time for questions. Let me see if, so as I said, there are similar expressions for plaquette-plaquette correlations. So if you take two plaquettes, look at the Wilson loop for one, take the Wilson loop the other, take the correlation of these. How does this behave as the distance between the plaquettes becomes very large? This is a way of testing for what's called confinement. And there are expressions for those. There is something called the Tohoft loop in the industry, where again there are similar things. Now, you can ask what happens in dimension 2. In dimension 2, the theory is solvable in many ways. One of the solutions goes back to a paper of Gross and Witten, and in fact, one can recover those expressions from this point of view. In d equal to 4, there are some issues to be sorted out, topological. Can you add lattice fermions? It seems possible, but for that, you have to introduce complex structures on the surface, which I have not pursued seriously, but I see a way of doing it. I think that's it. Okay, thank you.